Well, folks, I forgot to say the secret word in Lecture 10 again. So let me say it now. In retrospect, retroactively, the secret word for Lecture 10 is spoon. So I'll try to get better and say a secret word in this one, but anyway. Okay, so Lecture 11, more modular arithmetic and integer roots of polynomials. So I'll be showcasing how modular arithmetic has many useful applications to ordinary arithmetic in this lecture. And I really like the first couple pages where we're looking at things you can do with modular arithmetic to study questions of divisibility, especially for decimal representations of numbers. So what do we mean by decimal representation of a number? Well, we mean it has a base 10 representation, right? We use this, it's so drilled into us we hardly even think about it, right? But when we write n is equal to like ak minus 1, a1, a0, right? And those are numbers taken from 0 to 9. This is the base 10 representation of n, right? And what that means is that n is equal to ak to the 10 to the power k plus ak minus 1, 10 to the power k minus 1, plus all the way down to a1 times 10 plus a0, right? a1 is in the tens place, a1 is in the ones place, as we say, right? But you could also talk about a base b expansion of a number, right? Where you're using your digits, which is a bad word to use here, but sorry, I mean, digits is, that has a sort of a base 10 idea in the very language there, right? But anyway, I'm going to get over it and just call it digits. So the base b digits, ck through c0, these have to be taken from 0 through b, all right? And then you could write n is equal to ck minus 1, c1, c0 sub b to indicate that n is equal to this, all right? So to be fussy, if we want it to be consistent in our notation, I always write parentheses sub 10 when I'm using the ordinary decimal expansion, but I'm not going to do that because it's really annoying. Okay, so first application. We all learned when we were kids the rule of nines, right? The rule of nines. And what does the rule of nines say? It says that if you look at the decimal expansion of a number, right? It's divisible, that number is divisible by 9 if and only if 9 divides the sum of the digits, right? So, let's see here. So, here's the reason that's true. Notice that 10 bar, so first of all, the first idea here is to study divisibility by 9, we need to calculate what n bar is in Z9. See, because Z9 is all about division by 9, right? So the remainder of n bar in Z9 will be the remainder of n upon division by 9. And we'd like that to be 0, right? If we want it to be divisible by 9. Anyway, so here's the point. So 10 bar is equal to 1 in Z9, which means 10 to the power j is also equal to the equivalence class of 10 to the power j is also equal to 1 in Z9. So if we calculate the equivalence class of the number with decimal expansion ak through a1, a0 like that, we're calculating the, in Z9 this quantity, right? But remember, 10 to any power is congruent to 1, so using properties of modular arithmetic, these guys, well, first of all, it breaks into the sum of the products, right? And then all of the tens just go to 1, so you get this plus this plus this plus that. You get the equivalence classes of the digits taken separately, added in Z9. But then you can bring them all together, like that, right? And so what we see then is that n is congruent to 0 mod 9, if and only if the sum of the digits is congruent to 0 mod 9. So it's actually a little bit better than the rule of nines, right? Because we can reduce the digit sum modulo 9 to discern if 9 divides the product of the digits. 9 divides the decimal expansion, ak through a0. So for example, here's an example. if we have n is equal to that number, 3, 4, 5, 6, 7, 7, 8, 0, 9. What is that? 2, 3, 4, 5, 6. 345,677,809. Well, then the digit sum here is 3 plus 4 plus 5 plus 6 plus 7 plus 7 plus 8 plus 0 plus 9. And basically, if I'm working modulo 9, I can drop 9s in here, right? 4 plus 5 is 9. That's 0, you know. This is 28. That's 9. So I just grouped it over here. I'm thinking of it. That's where those numbers are coming from, right? But you notice that the 9 drops to 0, and this 28 is congruent to 1 because it's 27 plus 1. So that drops to 1. Again, the 9s drop to 0 in this calculation. And so we get 4. So no, this number is not divisible by 9. In fact, if you were to divide this number by 9, it has a remainder of 4. All right? So it's pretty neat, actually. And that's, again, easily derived with modular arithmetic. Here's an analog of the rule of 9s for what's called an octal number. I worked for the Navy for a year, and you know, one of the banes of my existence that year was, well, it wasn't really a big deal for me, but for other people it can be. You get data, and sometimes you don't know if it's written base 10 or base 8. And the annoying thing about base 8 numbers is they kind of look like base 10 numbers because they don't have weird symbols in them, and they're not just zeros and ones. You know, you see zeros and ones, you're like binary. But base 8 can have digits that go 0, 1, 2, 3, 4, 5, 6, 7. There's also something called hexadecimal, which uses A, B, C, D, E, and F to denote the numbers 10, 11, 12, 13, 14, 15. But anyway, octal is kind of annoying in that it looks like decimal if you're not. Well, it looks like decimals. So anyway, so what's the sort of rule? There's a rule of 7s in octal. So an octal number would look something like AK, A2, A1, A0 sub 8, which means A sub k to the 8 times A to the 8 to the power k, dot plus 8, A2 times 8 squared plus A1 times 8 plus A0, right? And when we reduce this mod 7, because 8 to any power is congruent, 8 to any power, the equivalence class of that is just 1 bar. So all of the 8s drop out, and we just get the sum of the octal digits. And so that's kind of your like rule of 9s for octal numbers. It's a rule of 7s, yeah. So for example, this octal number 3420137 base 8 has n bar equal to 3 bar plus 4 bar plus 2 bar plus 0 bar plus 1 bar plus 3 bar plus 7 bar in Z7. And so you group things together and you get 6 bar. So, yep, that number is not divisible by 7, by the octal rule of 7s. So there you go. There's all kinds of fun things like this, right? Like you can look at a rule of 11s for decimal numbers. Maybe I'll give you that as a homework problem or something. There's a lot of things like this you can do. Let me look at some other problems that are of similar nature, but a little bit different here. How many digits? Just keep playing these games here with another game to play. How many digits in the base 10 decimal representation of n do we require to decide if 40 divides n? So let's see here. 40 is 8 times 5, which is 2 times 2 times 5. And so in order to get a 40 in a power of 10, I need 10 cubed, right? So in order to decide divisibility by 40, I'm going to look at Z40, right? So notice that 100 is 20 bar in Z40, but 1,000 is 0 bar. And 10 to the j, in fact, is 0 bar for j greater than or equal to 4. And that's pretty much it. So modulo 40, we can take any integer, right, like this, and it just drops back to a2 times 100 plus a1 times 10 plus a0, which is congruent, which is equal to, rather, 20 a2 plus 10 a1 plus a0 bar, all right? And so we find then that n with this decimal expansion is divisible by 40 if and only if 20a2 plus 10a1 plus a0 is equal to 0 bar in Z40, right? So it's kind of neat. In other words, all you need to do is to check if 20 times a2 plus 10 times a1 plus a0 is congruent to 0 mod 40, right? So, long story short, we only need the 3 lowest digits to decide if a number is divisible by 40. So it's kind of cool. Let's look at another example. To find the lowest digit in the decimal expansion, all right? What can we say? To find the lowest digit in the decimal expansion, aka the ones place, we need only calculate n bar in Z10, right? Because the ones place, if we reduce mod 10, is all that's left. And so let's apply it. Let's find the one digit in n, which is equal to 9 factorial plus 11 factorial plus 13 factorial. This is a very, very big number, right? But if you start thinking about these numbers, right? 9 factorial, and you've got 11 times 10 times 9 factorial for the 11 factorial, right? 13, it's got 13 times 11 times, 13 times 12 times 11 times 10 times 9 factorial, right? And so, first of all, clearly this one and that one is 0 because there's a 10 in there. As soon as you get a 10, mod 10, any multiple of 10 is 0, right? But 9 factorial is no better because when you expand it, it's got a 2, and it's got a 5, so 2 times 5 is 10, so the 9 factorial is also 0, right? Now if you start thinking about it, oh, I knew that already, because as soon as factorials get to 5 factorial, there's always a 0 at the end of the digits, right? So like 4 factorial is 24, 5 factorial is 120, and then 6 factorial is 720, and then 7 factorial is 5040. There's always a 0 at the end of factorials past 4 rather. So okay, that one wasn't too interesting. I mean, we could have solved my first example here, and first sub-example in example 4 with just, common sense. Maybe this one's a little more powerful. 3 to the 10th, 7 to the 3rd power, 2 to the 8th. Let's find the one digit. So we're going to reduce mod 10. So I've got 3 squared to the 5th. I've got, get my 3 to the 10th. Now 7 is minus 3 mod 10, right? So I can change that 7 to minus 3 to the 3rd. And 2 to the 8th is 2 to the 4th times 2 to the 4th. I'm not sure why I'm doing that. I just mess around sometimes. So 3 squared is 9. 9 is minus 1. So I got minus 1 to the 5th. I got my minus 27. I got my 16 and my 16. But 16 I can reduce to 6 because 16 is congruent to 6 mod 10, right? So that gets us down to minus 1 times minus 27 is 27 bar. And 27 is congruent to minus 3. And minus 18, so that gives you 3 times 6 is minus 18. And then minus 18 is congruent to 2? Oh yeah, if I add 20, that's congruent to 2, which is congruent to 12, which is then simplifying down to 2 bar. So the ones digit in this guy is 2. Yeah, that's kind of neat, right? That's kind of neat. All right, so we could keep doing those kind of neat problems, but the show must go on here. So next up we have polynomials with integer coefficients, all right, like that. And I'm going to define a reduced polynomial, I'll call f tilde, where what I do is I take the equivalence class of each coefficient mod m rather. I'm using n for n as in nanu for the power of the degree of the polynomial rather, and m as in modulus for the modulus. So suppose there exists an integer root for f, such that f of c is equal to 0. Then notice that the reduced polynomial will also end up giving you, if we plug in the corresponding equivalence class mod m of that root, c bar, let's say, plug it into the reduced polynomial, do your modular arithmetic steps to get back to this, but that's exactly f of c. So the reduced polynomial evaluated at the integer roots equivalence class will be equal to the polynomial evaluated at the roots equivalence class. Actually, this calculation is true no matter whether c, this calculation is true whether c is a root or not. But when c is a root of f, when f of c is equal to 0, we see that f tilde of c bar must also be equal to 0 bar, right? So this is nice because what this means is that if f tilde of c bar is not equal to 0 for each c bar in M, then by the calculation above, there does not exist a integer root of the original polynomial. Does that make sense? So because if this happens for each one, that means that there couldn't have been, like if there was a integer root out there somewhere, then it would force the, there must be some equivalence class mod m in which that c fits, and that equivalence class would make this be 0 bar. And if it's not 0 bar for every possible c bar, then it must be that there wasn't such a c. So here's an example. If we look at x to the 5th minus x squared plus x minus 19, and we look at the reduction mod 4. Now you might wonder why we did mod 4. I think if you tried mod 2, if I try with mod 2, I get like 1 minus 1 plus 1 plus 1. So like f tilde of 1 bar mod 2 is 0, so this method breaks down mod 2, and something bad happens with mod 3 as well. Mod 4 is the first one that we're successful. So anyway, here it is. So reduction mod 4. So first of all, minus 19 plus 20. 20 is 5 times 4, right? Is 1 bar. So this is the corresponding reduced polynomial with coefficients in Z4. And then if I look at f tilde of 0 bar, f tilde of 1 bar, f tilde of 2 bar, f tilde of 3 bar, all that means is, of course, I plug in the number 0 bar, 1 bar, 2 bar, 3 bar, and Z4 into the formula here. I get 1 bar, 2 bar, 3 bar, and 2 bar. None of those are 0. Therefore, this guy does not have an integer 0. So this is irreducible over Z. So this is the other method I was talking about. In addition to Eisenstein's criteria, this is the other helpful way to prove something's irreducible. All right. Well, I should be careful. I guess that doesn't... I should be careful here. I don't think that proves it's irreducible over Z. What it proves is... I shouldn't say that. I don't think it says that, actually. Thus, this has no... integer zeros. All right. I guess I should entertain the possibility that you have, you could have a quartic and a cubic, perhaps. I don't want to get into all that. I'll leave that for your abstract algebra course, but let me dial it back here a bit. It says that it has no integer 0. That's what we proved. All right. I think I came to the light in the next example. Example 6, in terms of not overstepping my bounds. Show f of x is x to the 7th plus 9x plus 3 has no integer roots. All right. So we can look at reduction modulo 2 in this case, and I think it's going to work. So 9 bar is 1 bar, 3 bar is 1 bar, right? If I plug in 0 bar into this guy, I get 0 plus 1, which is 1 bar. Plug in 1, I get 1 bar plus 1 bar plus 1 bar, which is 1 bar mod 2. And there you have it. This polynomial has no integer roots. Now I should mention Jones and Jones, Elementary Number Theory, page 45, mentions this bad boy right here, x squared minus 13, x squared minus 7, x squared minus 221. This guy has f of x congruent to 0 for some choice of x, all right, mod n for every possible modulus, all right, which means that f tilde of t has no 0 in Zn, no matter what n you'd pick, and yet you can prove that this f of x is irreducible over z. In other words, it has this f of x has no integer zeros. The zeros of this are easy enough to see, like square root of 13 plus or minus, square root of 17 plus or minus, the square root of 221 plus or minus. None of those are integers. All right. So what this shows is that the method of example 5 and example 6 is only good for showing, I shouldn't say irreducibility either, it's only good for showing the non-existence of zeros. Okay, non-existence of integer zeros. In other words, it speaks to, and on the flip side, reducibility over Zn does not imply a reduction over Z. All right. Okay. Final example for this hopefully shorter lecture. Final 2 examples. So x equal to n squared. All right. We talked about this before. You got a perfect square, right? Well, the claim is then x is equal to 0 bar or 1 bar in Z4. Let's see why this is true, okay? So if we have x equals to n squared, that means x bar is n bar squared, right? And so in Z4, we can calculate that. There's 0, 1 bar, and 2 bar, and 3 bar to check. And when you plug them in, you get 0 bar, 1 bar, 0 bar, 1 bar. So if we have a perfect square, then division by 4 either gives us 0 or 1. So this wasn't too hard to prove earlier, but this is easier. All right. So here's a different question. What are the possible remainders for a perfect square upon division by 10? Oh, in other words, what are the possible ones digits for a decimal number which is a perfect square? So we'll look at x congruent to n squared mod 10 by studying x bar equals to n bar in Z10, right? And let me put it up here. So you got your 0 bar squared is, well, 0, let me just drop the bars for a second here. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, which is congruent to 6, 5 squared is 25, which is congruent to 5, 6 squared is 36, which is congruent to 6, 7 squared is 49, which is congruent to 9, 8 squared is 64, which is congruent to 4, 9 squared is 81, which is congruent to 1. So if you sort through this, the only thing we get from squaring equivalence classes, mod 10, is 0, 1, 4, 5, 6, or 9 in terms of their congruence classes. And so this is the possible choices for the ones digit in squares, right? It doesn't matter how big a number you take, right? Let's try it. 368 square it. What do you get? The digit's 4, right? 551 squared. What do you got? Last digit's 1, right? 873 square it. What do we got? Last digit's 9. It doesn't matter. We can do this all day long, right? whatever you do, the last digit's always going to be 0, 1, 4, 5, 6, or 9. So it's kind of cool, isn't it? So we could play this game for other things, right? We could figure out what are the possible digits. What's the possible ones digit for a cube? And you could figure that out by just looking at 0 bar, 1 bar, 2 bar, all the way out through 9 bar, mod 10. That would immediately tell you what the possible ones digits are for a cube. So I hope you start to get a sense that if we really master this idea of modular arithmetic, there's all kinds of concrete questions about arithmetic that we can settle that would otherwise be, I think, much more formidable. And this is part of Gauss's genius. Gauss was a master. He mastered these ideas of congruence, these congruence calculations, and it's what allowed him to write his masterpiece when he was much younger than me, half my age, less than half my age, sadly. But anyway, all right, so next up, lest I forget, the secret word for this lecture is, Pokemon. Yes, Pokemon is the secret word for lecture. What are we on? What lecture are we on here? Lecture 11. All right, thanks guys.